Welcome everyone to our Reading Groupoid. In this 10th lecture, we have the pleasure to have here Asier López-Gordon from IMPAN, who will talk about an introduction to the algebroids. So thank you, Asier, for accepting our invitation. The floor is yours.
Thank you, Oscar. So yeah, my goal today will be to introduce the notion of Lie algebroid, specifically the notion of Lie algebroid of a Lie groupoid and the general notion of Lie algebroid, and present some examples. So without further ado, I'll start by reviewing how we define the Lie algebra of a Lie group. Probably several of you know this, but just in case, if we have a Lie group, we consider the set of vector fields on G and the subset of left invariant vector fields, which means that if we act by the push forward of left translations, they do not change. By the way, everything that I will say today, left invariant, in some references, they instead take it as right invariant, but well, at the end of the day, it will be a question of changing the order of things, or in the case of groupoids and algebroids, interchanging the roles of the source and the target. So conceptually, it's all the same. So we have the standard Lie bracket of vector fields, which is just the commutator of the vector fields as differential operators. And by essential properties of push forwards and Lie brackets, we have this property. We can see that left invariant vector fields are a subalgebra. Sorry, this should be this Gothic X. Well, you get the set of left invariant vector fields is a subalgebra of the set of all vector fields, meaning that the Lie bracket of two left invariant vector fields is again a left invariant vector field. And moreover, as real vector space, the set of left invariant vector fields on the Lie group is isomorphic to the tangent space at the identity of the group. And we can check this by defining an explicit isomorphism given by this expression. And we see that this is an isomorphism because it has an inverse. And well, it is straightforward to check that indeed the image of this map is a left invariant vector field. We can endow the Lie algebra. So we define we endow the Lie algebra of the Lie group with a Lie bracket, precisely by the restriction of the bracket of left invariant vector fields. And sorry, I didn't say it, but it's just the tangent space at the identity. Okay, so what we will do for Lie groupoids, we will try to generalize this notion. Of course, there are several intuitive ways that we can think of Lie groupoids. And one of the ways that it's usually said is that Lie groupoid generalizes Lie groups in having, instead of one object, multiple objects. So as we know, we can see a group as a groupoid over a single object. So well, in a sense, this is what we will take into account to generalize this notion of Lie algebra to Lie algebroid. So left invariant vector fields on a Lie groupoid will be the subset of vector fields on the total space which are tangent to the T fibers, meaning this, and with such that for each pair of composable arrows acting by left translation of G on the tangent on H is the same as evaluating the vector field on GH. And well, we will use the same notation for left invariant vector fields. And we can again see that they close a Lie subalgebra of the algebra of vector fields on the Lie groupoid with the usual bracket. So essentially, we have to check that it verifies these two conditions, tangent to the T fiber and the condition on the how we act by left translations. So tangent to the T fibers can be re-expressed as follows by the definition of the tangent map. So for each pair of vector fields, if we take the Lie bracket, and by definition, we can see that it again is a tangent to the T fibers. So this is completely straightforward. And similarly for the second condition, for its fixed element of the Lie groupoid with source X and target Y, left translations are a diffeomorphism from the fiber at X to the fiber at Y. And for each pair of vector left invariant vector fields on the groupoid, the push forward by left translation maps the restriction of the vector field on the X fiber to the target fiber at X to the vector field on the target fiber at Y. And well, using since these two vector fields are tangent to the fiber, and the fiber is a submanifold, the restriction of the bracket is the bracket of the restrictions, and then we use the property that relates push forward by diffeomorphism with the Lie bracket, and then the assumption, well, we see that the second property also holds. So how we will define the Lie algebroid of a Lie groupoid? First, we will define a vector bundle, which will be the kernel of the tangent of the target restricted to the image of the identity map. Recall that U is the map that goes from the base space M to to G, to the space of arrows, and gives us the identity arrow. Or well, you can express this as a pullback by U of the kernel of the tangent of the target. And as usual, gamma of the vector bundle will denote the space of sections of this vector bundle. Of course, the projection, I said that this is a vector bundle over M. Of course, the projection is the natural one given by the restriction of the tangent space of G. And a next important lemma is that as vector spaces, the space of sections of this vector bundle is isomorphic to the set of left invariant vector fields of the groupoid. And again, we just check this directly by constructing an isomorphism. I'll use this arrow pointing to the left over some letter, some Latin letter to denote left invariant vector fields. So basically, for its section of the vector bundle A of G, we define the corresponding left invariant vector field at a point G by acting, so we take the left translation by G and its tangent map identity, acting on the section A evaluated on the source of G. And its inverse, it will be just evaluating the vector field, the left invariant vector field, restricted to the image of the identity map of the groupoid. And well, just we just have to verify that these maps have the images that correspond to the condition. Recall that we had this condition of left invariant vector field being the tangent to the T fibers, and it is clear that this is equivalent to the section this being a section of this, so I think it's clear. And similarly, the condition of how we act by left translations follows easily by properties of the properties of the tangent map and how we define the isomorphism. The next ingredient is an anchor, which is a vector bundle map from our vector bundle AG to the tangent bundle of the base manifold M, which is given for its for an element of the fiber at X of our vector bundle A of G is acting by the tangent map at the identity of the source map. And we can define a bracket of sections on the space of sections on this vector bundle, which satisfies a Leibniz identity in the following sense. So this formula like this will appear all along the talk. So Leibniz identity is similar to the usual Leibniz identity for Lie brackets, but taking into account that now we have to also apply the anchor map. So how do we verify this? First, we know that the anchor map applied to a section alpha can be re-expressed as the push forward by the source of the corresponding left invariant vector field. And also that the left invariant vector field and the vector field given by applying the anchor to the corresponding section are S related. Well, yeah, this is what I said. And also that for its function, we can write the associated left invariant vector field to any smooth function times a section is the same as the pullback by the source of the function times the left invariant vector field. So taking these two properties into account, how do we define the bracket of sections? So the bracket of two sections will be such that when we take the associated left invariant vector field is the same as taking as first taking the two associated left invariant vector fields and then taking the usual bracket of vector fields. And since we had, as we saw, we had an isomorphism, then we can apply the inverse isomorphism. So this will give us a well-defined bracket. Combining these two properties and the usual Leibniz identity for the Lie bracket of vector fields, we can verify this Leibniz identity. So summarizing, given a Lie groupoid, we will have, we will define its Lie algebroid as follows. We will define the vector bundle given by the kernel of the restriction to the identity of the tangent of the target, the anchor map, which is the tangent of the source restricted to this vector bundle, and the bracket of sections satisfying the Leibniz identity which we've just proven. And we will call this triple the Lie algebroid. Well, as usual, when it is clear, we will just call A of G the Lie algebroid of G. If we want to emphasize all the elements, of course, we could explicitly say what is the projection of the vector bundle and so on. Any doubts so far?
Everything is pretty clear.
Okay, thank you. Let me also recall that in some previous talk, I'm not sure, perhaps it was the one by Ruben, we introduced the notion of anchor of a Lie groupoid. Well, it's just the pair formed by the tangent and the source. So it goes to the product manifold of M times itself. And of course, we can see it as a vector, as a Lie groupoid morphism that maps any groupoid to a trivial groupoid. And it has a relation with the anchor of the associated Lie algebroid. Namely, recall that the algebroid, the vector bundle, was given by the kernel of the tangent of the target. So if we restrict the tangent of this anchor to the Lie algebroid, we have precisely the anchor of the algebroid. Well, I think this is clear by elementary differential geometry and linear algebra. By the way, let me insist that, yeah, here I'm using this definition. There are other definitions. Unfortunately, by the way, I should have said at the beginning, my main reference are the lecture notes by Riroya Fernandez from course he gives in his university. Well, this will be referenced in our usual lecture notes. So there are different criteria, and in particular, I think Mackenzie's book, unfortunately, uses a different criteria, but it will be essentially interchanging the roles of the source and target. So we've just defined Lie algebroid of a Lie groupoid. We can define a Lie algebroid in general as follows. So we will have a vector bundle, which is also equipped with a Lie bracket on the space of sections, and a vector bundle morphism of over the identity, which satisfies the Leibniz identity that we have been considering. Well, and we will keep calling rho the anchor map, and we will say that a Lie algebroid is integrable if it is the Lie algebroid of some Lie groupoid, up to isomorphism that I'll define later. So as it is well known in the case of Lie groups and Lie algebras, any Lie group has a Lie algebra, and given a Lie algebra, it has multiple associated Lie groups, and we have the universal cover and so on. Is there something similar for Lie groupoids and algebroids? Well, this was an open problem for decades, which was finally answered by Riloya Fernandez and Marius Kreinitz in a very long paper in the Annals of Mathematics. That's I'm of course not gonna cover today. And the answer is essentially sometimes. Not all Lie algebroids are integrable, and there are certain topological abstractions for the integrability. Okay. An important property of the anchor is that it preserves brackets. Namely, so we have the anchor is essentially a map from the space of sections of our algebroid to, well, we have defined it, sorry, as a vector bundle morphism, but of course, as any vector bundle morphism, it induces a morphism on the associated spaces of sections. So from sections of the algebroid to sections of the tangent bundle, that is vector fields. So if we take the Lie bracket of our algebroid and apply the anchor, that's the same as taking the anchors of the two sections and applying the usual Lie bracket of vector fields. And the proof, well, it's a slightly long computation, but it's straightforward, applying usual properties of the Lie brackets. So first we can apply twice the Leibniz rule to this bracket of brackets to express it like this, and the same for this other bracket. And as you can imagine, we will now apply the Jacobi identity. But on the other hand, we could also apply the line identity to this element, and sorry, this, well, the basically observing the equations from the slides before, we can directly observe the property. So I should now present some examples of Lie algebroids, and the most obvious example is the tangent bundle itself, with the anchor being the identity map and the bracket being the usual Lie bracket of vector fields. And this is, in fact, an integrable Lie algebroid, and its associated Lie groupoid is just the product groupoid. A related example is the any involutive distribution that is as a bundle of the tangent bundle, which is integrable, or well, such that the bracket of sections is closed on the distribution, as we know by the Frobenius theorem. This is the same as saying that this defines a foliation whose leaves are precisely the tangent spaces of the leaves are precisely the distribution. So, well, as we can imagine, this is also an integrable Lie algebroid. I'm not gonna present explicitly the Lie groupoid because we didn't see it before. It has different possible Lie groupoids that integrate it. One of them is the so-called holonymy groupoid. It's not very complicated, but well, since we didn't see it on the lectures on groupoids, I'm not gonna delve into that now. Another example is a Lie algebra over the singleton. Well, of course, this is also integrable by usual Lie theory. In fact, for any Lie algebroid, we associate the isotope Lie algebra at a point as the vector subspace given by the kernel of the anchor at that point, equipped with the Lie bracket defined by evaluating the Lie bracket of the algebroid on the point. And one could wonder if this is well defined. So let me show it. So by well defined, I mean that for any pair of sections that evaluated at the point X are these elements of the algebra, I will obtain the same result. So we consider sections alpha and alpha tilde, beta and beta tilde, such that alpha and alpha tilde at the point X are alpha X, and the same for beta. And well, since we have a vector bundle of any dimension, we can consider a local basis of sections, and this allows us to write any section as a linear combination of elements of the basis. So in particular, we can consider the section sigma given by the difference between the sections alpha and alpha tilde. And in particular, of course, this is a section that vanishes at the point X, that is all the components Fi are smooth functions that vanish at X. And we now just compute the Lie bracket, the Lie algebroid Lie bracket of the sections alpha and beta minus alpha tilde and beta. Well, by linearity, we can express it as this. This is just by definition the section sigma. We can express it in the local basis, and we can now apply the Leibniz rule for Lie algebroids. But we observe that here we have Fi outside the bracket, and here we have the anchor applied to beta. But on the one hand, if we now evaluate this expression at the point x, fi is a function that vanishes at x, so this will kill this component at the point x, and similarly, beta x by assumption is an element of the isotropy Lie algebra, but the isotropy Lie algebra is the kernel of the anchor, so this also vanishes at x. So this vanishes at x. That is, these two brackets are the same. And for the second argument of the bracket, well, since the bracket is Q-symmetric, the argument is completely analogous. So this shows that it doesn't matter the extensions that we use for defining this bracket. In the case of Lie algebroid of a Lie groupoid, we can express like this the isotropy algebra, because, well, recall that the fiber of the algebroid at x is the kernel of the tangent of the target at the identity, and the anchor map is the tangent of the source of the identity, so its kernel. So it's clear that we have this intersection of kernels. And recall that we had defined, I think this was in the lecture by Bartosz, perhaps, the vertex group, which is also known as the isotropy group, as the intersection of the source and target fibers at the point. So it is easy to see that, as one could expect, the isotropy algebra is precisely the Lie algebra of the isotropy group. And now let us consider again a general Lie algebroid, not necessarily integrable, so not necessarily coming from a Lie groupoid. And we can define the following bundle of algebra. So we have the isotropy algebra at each point, and well, we consider the union of all of them, but note that this in general will not be a regular or a smooth bundle, because I have not assumed that the anchor has constant rank. If it has constant rank, then we will say that the algebroid is regular, and we will have this short exact sequence. And moreover, we can see that in that case, the image of the anchor is an integrable distribution, and its associated foliation will be called the orbit foliation of the regular algebroid. And if it's not regular, that is, if the rank of the anchor can change, it is also possible to generalize this notion. So this is the Lie groupoids and algebroids are closely related with the theory of singular foliations. And essentially, one in this case can still define an orbit space such that the tangent of the tangent space of the orbit at the point x, it's the image of the anchor at that point, but these orbits in general will not be spaces of the same dimension. And we say that the Lie algebroid is transitive if the anchor map is surjective, so its image is the whole tangent bundle. And well, of course, this is in particular, any transitive Lie algebroid is regular. If we now let me introduce the notion of morphism of Lie algebroids over the same basis. So we have two Lie algebroids over the same base space, and we have a vector bundle morphism, which also preserves the brackets in this sense. and relates the anchors as follows. It is also possible to generalize this notion for Lie algebroids over different bases, but since we will not use it today, I decided to skip it. Another very important notion is the Atiyah algebroid. So recall that we extensively considered the Gates groupoid, also known as Atiyah groupoid, especially in the lecture by Ruben. So we have a principal bundle P over M with a principal group G. We define the Atiyah algebroid as the vector bundle given by the equivalence class of the or quotient in the tangent space of P by the action of G, and the anchor will be induced by the tangent of the principal bundle projection. So, well, we have our principal bundle P over M and our Lie group G acts on P. And by tangent lift, it also acts on the tangent of P. And we have the projection to Tm induced by the projection of P on M. Now we defined A as this quotient space. So for we can, for each element of the algebroid, for the quotient space, we can choose a representative here and project it. And this is how we will define the anchor. And similarly, the Lie bracket will be induced by the restriction of the Lie bracket of the vector fields on P to the set of G invariant vector fields. That is, vector fields which are invariant under the action of the Lie group. So similarly, we have on sections on the tangent bundle, we have a Lie bracket, the usual Lie bracket, and we restrict it to the, so we can consider in particular this Lie bracket for two G invariant vector fields, and by properties of the push forward and the Lie bracket, as we have seen before in other contexts, the Lie bracket of two G invariant vector fields will also be G invariant. So we can quotient by the action of the group and obtain an associated section of the algebroid, or vice versa. We have a section of the algebroid, and as a representative, we choose an invariant vector field and compute. So we can compute. We have two sections. We choose their corresponding representatives, which will be G invariant vector fields. Their bracket will also be a G invariant vector field, so it will then induce a section of the algebroid. Well, I think it's clear how it's defined. We can see that this is precisely the Lie algebroid of the Gates groupoid that we talked in previous lectures. So since this is a very important algebroid and groupoid, I will explain it in more detail. So let me recall that the Gates groupoid is the product manifold of the total space of the principal bundle quotiented by the diagonal group action. And the target map of an element of this space, so that is a point on the space of arrows of this groupoid, is an equivalence class of pairs of points on P quotiented by the diagonal action, and the target consists of taking the any representative and on the so the element U we project it by the principal bundle projection, and analogously for the source, but for the second element of the pair. So the tangent map will be related with the projection on the first factor of the product manifold, and the identity associates to a point X on the base manifold M, an equivalence class of the pair U with respect to the diagonal action. So the fiber of the algebroid at a point X is by definition the kernel of the tangent of the target evaluated at the identity. So well, we can see that this we can express this as applying the tangent of the quotient map given by the diagonal action over the pair of vector fields 0 and a vector field on the point U over P. And by the diagonal action, we can relate the tangent vector 0 wide at the point U to the vector 0 acting by the tangent leaf of G of Y at this other point. But this is how we see that this is indeed the vector bundle that I said on the previous slide. And well, we can see that sections of this quotient of the tangent space by G are precisely correspond to left invariant vector fields. And in turn, for its left invariant vector field on the principal bundle, we define a left invariant vector fields on the principal on the gauge groupoid, sorry, as follows. So well, this like this we see that this precisely corresponds to the Lie bracket on the Atiyah algebroid. And well, by G invariance, yeah, I think it should be clear that this is precisely the Atiyah algebroid. Any doubts so far? Okay, so okay, thanks. Another observation related with this is that an integrable and transitive Lie algebroid is isomorphic to the Atiyah algebroid of some principal bundle over the same base space M. So to prove this, let me recall that in the third lecture, Ruben showed several important results concerning the gauge groupoid and locally trivial groupoids. So one of these results is that being locally trivial is equivalent to the fact that the restriction of the target map to the source fiber is a surjective submersion, and also that any locally trivial Lie groupoid is isomorphic to the gauge groupoid with well, principal group being the vertex group and this being the total space. So, well, taking those propositions into account, it is kind of straightforward to prove it. So we have being integrable. So if we have the algebroid, being integral means that it's the Lie algebroid of some Lie groupoid. And let me recall that transitive means that the anchor is surjective. So the restriction, but the anchor of the, in the case of a Lie if the Lie algebroid is from a Lie groupoid, the anchor is just the tangent map of the source. So, well, by usual results from differential geometry, sorry, probably here I mix the source of the roles of the source and target somehow, but well, the idea should be clear. And so the target map is a surjective submersion. And well, then we just use the propositions that I said. And another example, which is quite interesting and related with the examples we saw of the groupoids, is the action algebroid. So we have a Lie algebra that acts on a manifold that is for each element of the Lie algebra, we associate a vector field on the manifold, we will call the infinitesimal generator. And then we can define the so-called action algebroid as the vector bundle given by the product of the base manifold times the Lie algebra. So this is a trivial vector bundle globally. And the anchor is associates to its element of the algebroid, so its pair given by a point on the manifold M and an element of the Lie algebra C, associates this element of the tangent bundle, where this is just the infinitesimal generator of the action of G evaluated at the point X. And the Lie bracket is defined by identifying sections of this trivial bundle with smooth functions from the base manifold with values on the Lie algebra. And as one could expect, this is precisely the Lie algebroid associated with the action groupoid given by the action of a group, of a Lie group. And well, this turned out to be a shorter talk than I thought at the beginning, but this is all that I wanted to tell for today. So thanks for your attention.
So thank you, Asier, for your pretty nice talk. It was pretty clear. So now is a good moment for questions. If you have any, please go on. Well, I have one. Could you please, maybe Asier, if possible, comment a little bit, maybe if you know, like any relation between singular foliations and Lie algebroids?
Well, I'll try. This was, I mean, essentially, the technical details right now I don't know, but essentially the idea is that we will have an anchor map that we will not have constant rank, right? So this means that the tangents, that the orbits will not have constant rank. So we will not have unusual foliation. That is, we will not divide our total manifold into leaves that are submanifolds, all of them of the same dimension, but rather it will be, I think, what is called a stratified space, in which not all the leaves are of the same dimension.
Yeah, but well, precisely, my question was like, from what you said, it is clear that given a Lie algebroid, you can associate to it and a singular foliation, right?
Yes.
So is the converse also true? Like, given a singular foliation, can you associate to it a general Lie algebroid such that the foliation is induced by the anchor?
I would say that probably yes. Mm, because essentially, in
Well, the problem for me is like looking like into this direct way of Stefan and Sussman. Well, there are several definitions, right? But following the definition of Stefan and Sussman, actually the problem is like when you try like to develop the usual theory, the tangent to the foliation is not a subbundle of the tangent bundle, right?
yes.
Because for sure it has non-constant rank, but
But
it is also
there's
true that
this notion of general distributions that are so well, like there are general bundles where each fiber can have different rank.
yeah, the generalized bundles, but that is not only algebroids. At least globally. But well, but maybe I don't know. It was just I was just curious because there are people like using this equivalent definition of singular foliation as a submodel of the space of compactly supported vector fields and so on. So maybe using that point of view, I guess you can like relate to the algebroids in some way. There is a famous paper I can search.
Okay, thank you. I should check. Yeah, I mean, sometimes also when working with these singular objects, what people do is work with things that are singular but not so singular, let's say.
Yeah,
So
that's
impose some sort of restriction, and maybe, let's say, you have some sort of singular foliation but not extremely singular, then you can associate a Lie algebroid, but I should check.
Yeah, it is not. I mean, it is not a trivial thing at all. I mean, and a lot of people working on these things is, well, for sure, it's pretty technical. But I was just curious, and
Yeah, for sure, it's a very
because
interesting question.
for sure, in the regular case, everything is pretty clear because you have Frobenius integrability and so on. But in the singular case, indeed, I guess like people, the other day I was like, reading this the great book on Poisson geometry by Kreitnik and Ruiloja and so on, and they have an appendix of singular foliations. And at some point, why they say is like the proper way of studying. Well, the proper way. There are several ways, but one very usual way of studying singular foliations is using shifts, not only generalized bundles. They say somehow that generalized bundles are not the best way to study that. But
I see.
it's an interesting topic somehow. So
Yeah,
thank you,
for
Joseph.
sure. Yeah, no problem.
Is there any more question? Well, so thank you, Asier, for your pretty nice and clear talk. And well, see you next week.
Actually, the
Well,
week after.
no, next week. Well, yeah, because there's this congress in Tenerife first. Okay, so thank you. And Manolo, if you could stop the recording now.
Stop the